PADS Professional is a complete design suite for the single engineer or small design group. Design challenges being faced by engineers today are getting more and more complex. And it's not just the electrical, it's also dealing with the mechanical interfacing. So let's see how the PADS Professional Design Suite can solve these challenges for the design engineer. In our example today, we're going to be showing a smart drill. You'll see here the mechanical engineer has designed the board outline and placed critical mounting locations for us. Adding parts to our design should not be a complex task. With the PADS Databook application, your data can come from your corporate ERP system or an engineering database that you've set up. And a little bit later, we'll talk about part supplier integration. So here we're searching for a component that we want to add into our design using parametric searching functions. We're first going to look for a little voltage regulator to add into our design. By picking the manufacturer's part number, you'll see we find the exact part that we want. We can then see the symbol and drag that item onto our schematic. Once it's been placed in our schematic, we can quickly hook it up using right-click Draw Net features. From there, we're going to add two additional parts into our schematic, the adjustment resistors to define the voltage for this output regulator. And again, we're going to type in the value in our databook window. It'll find the part that we're looking for. We can drag that onto our schematic and add the additional component as well. You'll notice as I move through the design that the tool has a nice alignment feature that allows me to make sure my components are perfectly aligned. Now that the circuit has been added, to facilitate faster design, we're going to reuse design content from another project. Very simple to do. Open that project in another PADS Professional Designer window. You'll see here I'm going to copy the hierarchical block information from that design, go back over to the design that I'm working on, and paste that in there. I can then grab that symbol and drag it onto my schematic, and then using connection automation, connect up the pins between the two devices. We can also automatically add the net names by clicking over the hierarchical block and choosing Add Net Names to connected nets. Let's take a quick look at all the blocks that I've added to make sure everything's there. We can double click into the first one and see the reuse information that I carried over from the previous design. Then we can look at the additional blocks that I've created to make sure everything is done. The next challenge I have is to verify that none of my nets on my board are going to have signal integrity issues. So let's analyze one of the nets that I have a concern with. Directly from the schematic, I can push this net into our hyperlinked signal integrity tool that comes with PADS Professional. Because I pulled all this part information from part database, all my model assignments have already been added to these parts. So I can quickly go in, simulate that net, set the frequency to the proper frequency I want to look at. In this case, it's 32 megahertz, and see that I definitely have some concern here with this net, a lot of ringing and overshoot. To solve this problem, I'm going to go ahead and choose to add a series resistor to slow down the edge rate a little bit in the reflections. This is simple to do by adding a component. I can choose to go in and set the value, or I can use the termination wizard inside of hyperlinks to determine the value for me based on board stack-up information or driver receiver pin characteristics. Now that we've set the value, let's go ahead and simulate again and see what the signal looks like. You can see here it's clearly reduced the high frequency noise on the signal and reduced the ringing and overshoot. So let's go ahead and continue with this. In addition to adding passive components, we can also look at the stack-up and see how we can affect the signal integrity. So looking at our basic stack-up, we want to make some adjustments. Let's separate some of the internal ground plane layers and set some of the ground plane layers closer to the signals, which will improve our signal quality as well. In doing this, we're going to run the termination wizard again because the impedance characteristics of our traces have changed, which is more than likely going to change the value of our resistor, which you can see here it does. It changes to 30 ohms. We'll go ahead and simulate again and see that our signal still looks the way it should. Let's go ahead and continue with this 30 ohm resistor. I've done a search and found that we don't have one in our database. Let's move over to PartQuest to find our new component. To start, we'll type in a few component parameters in the search bar. Once we find our part, we can look at the basic parameters available in DigiKey. We can also see that a footprint, symbol, and 3D model is available for this component. With our part found, we can now add this to our design by simply dragging and dropping the data from PartQuest into PADS Designer. After a few seconds to download and import into our library, we can now see the part is available for us to add to our design. Adding the part to the design is very simple. You simply right-click over it, click Place, and drag it onto the schematic. We can then go over to our Properties window and see all the property information that was delivered with the component. Let's go back over to PartQuest and search for an additional component we need for our LiPo battery charge circuit. This time we notice there's no symbol, 3D model, or footprint assigned to the part. So to move forward, we need to create a symbol and footprint. Within PartQuest, there's a very comprehensive IPC 7351 standard calculator. To start, we'll choose the appropriate template for our device, in this case, a discrete. Next, we'll select a package shape, then we'll move on to entering the actual dimensions of the package. We'll notice as we add the dimensions, the package will automatically start building in our preview window. Clicking continue, we can start adding pins. If needed, we can set up groups of pins for devices where all pins are not the same. As you can see, we are given a graphical picture of terminal types. For our resistor, we're going to use the wraparound pin style. If help is needed to select the proper pin style, you can hold your cursor over the eye icon to see where definitions can be found in IPC and JEDEC standards. Moving on, we will select the terminal position, terminal shape, and lastly enter the dimensions for the physical terminal. By entering the pin geometry from a specification, the calculator will build the pad for you based on IPC standards, alleviating the need for us to hand calculate the pad geometry. Clicking continue, we will now set the pin numbering direction, our pin number scheme, part outline polarization, and lastly, the package body type used by the device we have chosen. On our last page, we can choose the target design density. There are 3 IPC options available for calculating the pin geometry and body outline. During this step, it'll also do a validation check on our component. Returning to our search, we will see a thumbnail of the footprint we just created. We now need to create the symbol for this device. We can create a new symbol from scratch by clicking on the Create Symbol, or in our case, we will choose a resistor from the many templates provided. Pin numbers will automatically be assigned based on the footprint we've assigned to this device. However, you can make adjustments if needed. With no adjustments needed, we'll click Done. This will take us back to our part where we can see the symbol and footprint are assigned to our selected component. In addition, we can add components to a project, which will make it easier for finding those devices later when we come back into PartQuest. In this case, I'm going to assign this part to my hand drill project. Now, if I go over to the hand drill project section, we can see a complete list of all the components that have been added to this project. Before I move on to generating a bill of materials, I want to make sure that all the parts in my design have the proper attributes so that I don't have any errors in my bill of materials or have to do any corrections afterwards. So let's go ahead and do a quick verification on all of our parts back against the database. You'll see here that most every component comes back with a green light, but I have one that seems to have missing attributes or the wrong attribute information. Let's click on that part and go visit it in the schematic and see that it's set to 3 megohm, which is not found in the database based on the other attribute information. So very quickly I can right click over that, do a search, see that the value is a mismatch. Go ahead and remove that condition and see that we find a 3.3 megohm resistor, which is what this is supposed to be. We'll go ahead and select that part, do an update, and fix the schematic. Now everything in our schematic is 100% correct. One of the big challenges engineers and companies deal with today is creating variants of their assemblies. This is very easy with PADS Designer. It has built-in functionality for doing variant management. You'll see here I'm going to add a new variant to this design for a low-end product. We then get a spreadsheet view of each one of those product lines, and then I can see all of the components, cross-probe back into the schematic to see where the parts are, and choose to replace or unplace that component. For this low-end product, we're going to remove the LCD display from the drill. As with everything we do, we have to document that. So for each one of our variants, we can go in and view that variant, and then I can produce a PDF output of that schematic design, showing that that part is not being loaded. In addition to seeing the basic schematic, I also have intelligence built in. I can pop into hierarchical blocks, and I can view attribute information on components, and I can also cross-probe nets in the PDF. Now that we've created documentation schematic, let's go back and create all the bill of materials for each one of the variants. Bill of material output is fully customizable and can be generated all at once. And we can produce an Excel file that can be directly imported into an ERP system. As the electrical engineer, I want to be able to control my constraints for the PCB layout if I'm not doing the layout. So directly from the schematic, I can open up this constraint editor application, which is the exact same information the PCB designer will see. You'll see here I'm going to create a power class with my power nets in it. And then I'm going to set up my appropriate trace width information for each of the individual layers, which can be done very quickly using this Excel-based environment. Additionally, we want to define spacing between copper objects in the design. So we can do that quickly again in our spreadsheet. I can set one cell, and I can use drag and drop methodology like I do in Excel to make it quick and easy. Lastly, I know I have some high-speed constraints in this design, so I'm going to go and set some high-speed length requirements for my nets. In addition to doing these basic things, we can also do area-based design rules and complex topology along with blind and buried vias and virtual pins. Now that we have all the rules created, we're going to move on into the layout. So let's go ahead and choose a template, start our design from the schematic, and take advantage of that mechanical engineering content. He's going to use his collaboration interface to generate output from an X in this case. We will then use our collaboration interface to import that data into our board design, making the process of creating the board outline and placing critical mounting holes extremely simple. Part of capturing the schematic allowed me to generate groups for components to make it easier for component placement. So here, using our Component Explorer, you can see I've got 3 groups of components. We can go ahead and drag those groups onto our PCB and do some placement strategy to make sure that we have enough space to place our parts and that the connections between those components are in roughly the right locations. This process facilitates faster placement of the component. Using further automation in PADS Professional, we can auto-place components and then adjust them as needed. Built-in schematic viewing technology allows me to view the schematic directly inside my layout tool. Using this view, I can select components in the schematic and have it cross-probe and find them in the layout for me to help speed up the process of component placement. Using the copy and paste feature, I can replicate circuits that are duplicates, which we're doing here with this resistor and capacitor circuit. So to mitigate the challenge of going back and forth with Mechanical Engineer, we can bring in mechanical features into the PCB tool. In this example, I brought in a piece of the drill to make sure I don't have any collisions when placing components. To make this more interactive, we can set up 3-dimensional DRC rules. Here we're going to set up component to mechanical design rule height requirement. So as I place this IC, I can clearly see when I have a collision with that component, or if I'm near a collision when it turns yellow. If we look at a side view of the PCB in the mechanical structure, we can see that there's an overhang of the board, and this is where the collision was occurring. So now we can place the part appropriately. We may not want to place all of our parts in 3D, but we can at least use the 2D and 3D view together. So I can still place some of my parts in a 2D environment, but I can also see what it looks like in that 3D environment. Another example of taking advantage of having the MCAD in the PCB world is I can see where parts are, again, overhanging the board where I may not have access to those components from the top, and I can adjust my placement before having to do iterations with the mechanical engineer. Now that we're done with our placement, I want to send the PCB information back over to the mechanical engineer just so he can do a verification that I placed like a connector in the right place. So using the collaboration capabilities in PADS Professional, I can output the entire PCB and all of its model information to the mechanical engineer. The mechanical engineer can then use the collaboration interface on their side to import all of my component placement information and verify if I've placed everything in the right locations. Clearly, he can see that I did not put the mating connector for the LCD display in the right location. Instead of the mechanical engineer reporting back to me that this connector needs to move in a certain XY direction, they can simply move the connector into the proper location and then send back a collaboration file. While in PADS Professional, I can import that collaboration file and see that that connector has moved to a new location. I can then choose to accept or reject this change based on my knowledge of assembly. We will go ahead and accept this change by typing in a note, sending it back to the mechanical engineer to let them know that this has been accepted. When I hit apply, the connector will now move to its new location. Now that the mechanical engineer and I agree on the placement of components, let's go ahead and move on to the routing phase of the PCB. Again, to facilitate faster design, I'm going to use routing automation capability in PADS Professional. To start out, I'm going to fan out a couple components so that I don't have to do this manually. After completing this process, let's go ahead and start routing. Using PADS Professional sketch routing technology, we can quickly route nets that would otherwise take 3 to 5 times as long to route by hand. As you've just seen, I routed 6 nets in about 1 second. For the next section we're going to route, I need to make some rule adjustments. I forgot to make some differential pairs and set up some high-speed constraints. Once we've defined our differential pairs, we need to go ahead and set our length requirements for the single-ended nets and the diff pairs. As you'll see when we start routing, length information can be seen in many different ways. We can show it here in the CES. We'll be able to see it on our cursor. We can use it for multi-trace tuning, or we can use it for manual tuning. With our rules created, let's go ahead and start routing. Using interactive, we'll start with our differential pairs. We'll then use sketch routing to route the single-ended nets from our IC to the connector. And very quickly, using the high-speed multi-trace tuning option, we can select these nets from the Net Explorer and then right-click in the workspace and choose Tune. To verify the nets have all been routed to the proper length, we can go to Analysis, Target Length, and see that each has been routed to its requirements. Next section of the board, I wanted to control the fan out of these capacitors. So I'm going to go ahead and route one of those in, and then using copy-paste technology, quickly replicate that onto the other capacitors. Next, we're going to define our plane areas on the board. Again, using automation, I don't have to draw plane shapes. With dynamic plane capability, I could just use the route outline, which already exists, as a plane area shape. In the case of this layer, I have 2 voltages that I want. So I'm going to have to draw in another plane shape. But again, using dynamic capability, the tool automatically floods the layer, and as I make adjustments to that shape, it will automatically fill it in. I also have a pin for this net that requires high current. So very quickly on the fly, I can select that pin, go and adjust the pad stacks for larger thermals without having to go into my library or pad stacks. Again, I can adjust the shape very quickly to adjust to make sure I have enough thermals for this net. Before moving on to manufacturing, I want to do some electrical verification and obviously DRCs on my design. So let's take a look at that net that I looked at earlier from the schematic level to make sure it's still electrically correct based on the routing that was performed in the design. We can take our design from the layout into hyperlinks. Once the design is loaded, I can select the net of concern, simulate it, and see that yes, indeed, the signal quality is as expected. While I was doing component placement, routing, plane creation, everything, there was DRCs being performed on the design automatically. But there wasn't detailed fabrication design rule checking being performed on the fly. One of the challenges many times overlooked is verifying your design for fabrication. PADS Professional includes a comprehensive set of design rules for design for fabrication. These can be run at any point in time during the design, but in this case, we're running it at the very end. From the DFF dialog box, you have full control over what layers are being checked, what types of objects are being checked, and what types of rules are being run. Here's a quick view of many of the design rules that are available for you to set. Proximity to signal, proximity to drill, proximity to solder mask, signal, plane, drill, solder mask, silkscreen, solder paste. Your rules can be saved into configuration files and then reused in various designs or between several different users. So to simplify the process of running your DFF rules on a new design, you can simply choose one of the schemes that have already been created and click Proceed to perform the action. Once the rules have run, you can go to your Hazard Explorer. There'll now be a DFF tab available. There you can see each category and if there's violations or not. In this case, we'll look at a couple of solder mask to proximity violations. You can navigate to them by simply clicking on them in the Hazard Explorer. It'll take you to that violation in the design. Once found, you can use the push and shove technology in PADS Professional to simply fix the issue. Not performing this level of verification can lead to fabrication delays, assembly delays, and possibly quality issues down the road. Before we move on to the last step in doing a board design, let's take a quick look at PADS Professional's rigid flex option. We'll start our design by bringing in mechanical data, which in this case is coming from NX, using the collaboration capability in PADS Professional. Using collaboration automation allows us to quickly bring in the board outline, the flex regions, and to mitigate any errors that may be caused by interpreting a drawing. With all of the board areas now imported from MCAD, we need to define the stack up for each one of the regions. This is done by simply selecting one of the regions, giving it a name, choosing stack up, and then from the stack up that was previously defined, turning off the layers or selecting the layers that are appropriate for that region. Stack up schemes can also be created and then assigned to regions to save time. Once done, we can then review the stack up graphically to make sure we've chosen the appropriate layers. The real power behind the flex capability in PADS Professional is the ability to define bend areas, review it in 3D, and use intelligent DRCs for verification. We'd start by defining our basic shape for a bend area, assign that to a bend region. This mitigates any issues with overlapping flex areas. We then set the bend radius for the shape and any of the other various parameters required for this flex region. Let's now take a look at the design with our bend in the flex in 3D. But more importantly, we can review the design with the mechanical enclosure turned on, and then adjust the bend area location and radius as needed. Something very important to flex design is understanding that when parts are placed in the flex region, you should not have square corners of any kind. As an example of this, we'll take a component that's on the rigid part of the board made with rectangle pads and move it down to the flex area of the board. Notice that the pad geometry is automatically changed to circular corners instead of square. With PADS Professional, this capability is built into the library component so that separate components don't have to be created for flex versus rigid. Like we mentioned before, it's not a good idea to place any square corners in a flex area. In this case, we need to route traces around a 90-degree bend. So we'll place in our first trace using interactive routing and adding an arc. We'll then use that trace as a template for creating the other ones in a couple steps. Using our hug trace feature, we'll select the pins we want to route, set the appropriate trace width and gap, and then choose the start and end point for the new traces. The tool will automatically add those in, and then we can finish them off at the end. Not common in all designs, but when you're developing a flex that terminates into a connector, you need to add a stiffener where the edge fingers will slide into the connector. With PADS Professional, you can build this into the actual footprint and then turn the feature on when needed in the design. And using 3D visualization, you can verify that it's the appropriate shape. When developing our first bend area for the Bluetooth board, we brought in the mechanical enclosure that the electronics will fit inside of. At any point in time, we can turn this on. We can look at cross sections and side views to visualize to make sure our flex circuits will fit appropriately in the design. With our design now complete, we can send a complete model to the mechanical engineer, view all of the electrical layers, perform any simulations that they need to. They can also now do a mechanical interference fit to make sure we've visualized everything appropriately. Of course, this interchange can happen at any time if changes need to occur during the design phase. Moving on to the last step of a board design, we need to output our data for fabrication. Just like any tool, we can output Gerber, but the most appropriate way to send data to a fabricator is via ODB++. It's a much more intelligent database format, and it includes additional information like for our flex design here that we reviewed at the end. So using manufacturing automation, we can set up our ODB++ output. We can save that off into a configuration and reuse it over again. PADS Professional includes a ODB++ viewer. So when done processing the data, it will automatically open the design in the viewer, where you can do last visualization checks on all of the content being included in the manufacturing output to ensure you're providing all the information needed for fabrication and assembly.